Hello. In this week, I want to dive into the groundwater flow module as it is part of the GRASS GIS open source software. So this lecture is a bit more special and a bit more specific because it's very concise just about this one module. So in a broader sense, it might be less relevant and not so interesting for you. However, I think it's a good opportunity to repeat a bit of the vocabulary and the terms I introduced in the past, and remembering what are the benefits and drawbacks as an example on the groundwater flow module in GRASS GIS. So the groundwater modeling tool in GRASS GIS is definitely not high-end. It was developed by Simon Gebhardt in 2007 and this master project at the Technical University of Berlin in Germany. And there surely is software that is more specialized for groundwater modeling, has a more convenient user experience, and provides you with a lot of tools for further analysis of breakthrough curves, of observation points, pumping tests, and so on, than it does by GRASS GIS, where you have to, rely on the raster, a lot of the raster and map analysis tools provided by the GIS system itself. However, I like the GRASS GIS groundwater flow module for educational purposes because it allows options and provides you insights in some aspects which are usually hidden by a kind of professional software, and because it still has a very slight learning curve. You have a graphical user interface, and as a geoscientist, you're working in this GIS surrounding, which you're probably already familiar with. So when we look at the discretization in space, the GRASS GIS groundwater flow module relies on structured meshes. So in a 2D, it's based on rectangles, and 3D, it's based on rectangular hexahedrons, which is just simply based because the groundwater flow module in GRASS GIS makes use of those raster maps. And well, raster maps are usually rectangles. So this is where we have the structured meshes. And then as a method, it is based on the cell-centered final volume method. So you hopefully still remember from the lectures about spatial discretization what finite volumes are and how it works. The cell-centered just simply means is that you approximate the variable in the center of the control volume, and then you still have the flexes through the surfaces of your control volume. And the chosen scheme here is especially valid for homogeneous as well as linear and rectangular volumes, which here is fulfilled because we work on structured meshes with rectangular grid cells, and we have an equal volume size in one direction, means there is no wider or shallower mesh, but all meshes have equal size. The X and Y direction can still be different, but in each direction, so in X or in Y direction, all cells have the same length or width. And this is here, because it's based on these raster maps, and this is how raster maps are structured in GRASS GIS. So this is fulfilled every time, and it's a very convenient choice here based on the numerical method. The discretization in time is an implicit Euler forward scheme, which means, hopefully you remember, it is unconditionally stable. Still, it also means that the error grows with increasing time step, right? Just because it's implicit doesn't mean it's accurate. As larger time step, as less accurate the solution will be, because it's a linear approximation. And interesting is, if you look in the contaminant transport module, so which is r.solid.transport, which is by the same developer and also is based on uses partly the groundwater flow module, you will see that it has a special hint or a trick to increase accuracy. So it's still implicit, but if you provide a time step that is larger than the time step that is suggested by the current vertical levy stability criteria, which you hopefully already also remember from last time, then it will automatically compute a suitable time step which fulfills the CFI criteria. And then, it is adding up time steps until your input time step is reached. And then the computation is done. Right, so here there is some internal time stepping. So you're not gaining pretty much from the implicit stepping. But of course, you don't have, your criteria is stable. But it's still internally computing a time step that fulfills the CFI criteria, not for stability reasons, but for accuracy reasons. We can talk about numerical dispersion. We had this before. It is a problem when we're talking about hyperbolic PDEs, which is the case for the advection term. So what you can do here is, for example, check the Peckley number, which you also remember from previous lectures, and reduce the grid size if necessary. The code itself does some stabilization of the advection term. So in the finite volume method, it uses some kind of weighting scheme. So to be more flexible, you can use a full upwind scheme. So we learned in one lecture what an upwind scheme is. So you're only using points which are upstream. So I used the example in this lecture going from a stream from left to right. So I'm only considering which are left from a point of interest and ignore everything that is right from a point of interest because of the advection. Still that, it might minimize numerical dispersion, but still numerical dispersion might occur. There's also another method which is called exponential upwind. You can decide which of those both options you want depending on the flag you're setting. There it's not a pure upwind, but it's an exponential weighting of the points with distance. Exponential weighting, of course. So this is also something to try out to see which works better depending on the scenario you're testing. But the standard application is the full upwind, which probably is also recommendable in most cases. Then the groundwater flow module in GRASS GIS usually applies iterative solution methods. So there are a couple of solvers implemented, dependent if you just have the groundwater flow module or if you have that coupled to solid transport. The iterative solution methods have the benefit that it's memory efficient, and the standard application, which is also the most recommended one, is the method of conjugated gradients, because it's based on matrix composition, is very well suited for those kind of linear system of equations as you achieve it by the groundwater flow equations. For the solid transport, it's recommended to use the biconjugated gradients. The matrix there is a bit more complex than on the pure groundwater flow module. So that's why the biconjugated gradients are recommended. You can also use the other ones, which are also partly implemented, not just in the groundwater flow module, but the GRASS GIS comes itself with a library to solve partial differential equations. And so it comes itself with a couple of solvers, and a couple are implemented here, and some are available to the groundwater flow module. So you could also choose a different method, but usually those ones give you the best convergence. So the stable solution is achieved in less iterations than the other ones. But of course you can try it out and look for differences. Every iterative process, and so this is very general here, it's not just about the groundwater flow module in GRASS GIS. Every iterative process usually has two kind of stopping criteria. I mean, it needs at least one, but usually has two. One is your convergence level. So what you're trying is in an iteration is, you start with the first gas with your initial conditions, you do your calculations, and then you compare the result to the first GAS, so your input model. And if this difference is too large, you're starting the whole process again, but now you use the result from the previous iteration as the initial conditions and do your calculations again. So, and this way you hope that if the solution is convergent, the error becomes smaller and smaller and smaller, so that the change between the two solutions of subsequent iterations become less and less and less. And at some point, they hopefully are less than the demanded convergence level, so what you set as a level of error that you're still okay with. But it might happen that solutions do not converge, or the conversion goes really, really slow. And therefore you have a second abort criteria, which is the maximum number of iterations. And you do this to avoid the deadlock of a computer, right? So if the solution does not converge, the computer would go on and on and on and on, because this convergence level is never achieved. And to avoid this, you always have usually have a second stop criteria, which is the maximum number of iterations. So now you could go and say, well, I could just use the maximum number of iterations, because if it converges, that's okay to me, and if it does not converge, it will abort at the same number, at this maximum number of iterations anyway. However, through the convergence level, you of course usually are faster, because if the solution converges, you reaches the level of convergence earlier than the maximum number of iterations, usually substantially earlier than the maximum number of iterations. Right, but those are two parameters you can provide the groundwater flow module in GRASS GIS, and you can vary those parameters and see how it influences your result, which is very interesting and very informative for you to learn, to understand how those kind of solvers work. There is for the groundwater flow module an input parameter which is called the relaxation factor. It only is relevant for two kind of solvers, if you use the Jacobi or the SOR solver. This is really a non-trivial task. Estimating this kind of factor a priori is difficult. As a rule of thumb, usually smaller than 2. Personally, what guess you can start with 0.5 or so. And then the idea here is that it's improve your convergence, so you can achieve convergence quicker. But the exact factor depends on the properties of your generated arrays in the linear system of equation. So it's an non-trivial task, and well, I'm not digging enough into the mathematics behind it during this lecture to give you an adequate answer to this one. So we'll keep it on that kind of level. You will also have the chance to apply a preconditioner. So preconditioning from a mathematical point of view is nothing else than a transformation. So you all might know from your basic mathematical lectures a matrix transformation and transformation in your coordinate system or things like this. So it's an mathematical operation from linear algebra. The idea here is to solve the problem in a way to make it more suitable for an iterative solver, to increase the rate of convergence, so that you obtain the stable solution, the convergent solution, within fewer iterations. There's something called the condition number, which can be theoretically computed. The idea here is to measure how much a function relates to small variations of the input variable. So it's kind of a sensitivity measure, and the idea here is during preconditioning to reduce this condition number. For you, more as a practitioner who wants to apply things and not worry so much about the mathematics behind it, you can use a preconditioner. It can increase your calculations. But you might also consider that calculating the preconditioner also requires computational costs. So it's a trade-off. It can help, but it can also increase your computational costs. So be careful most cases it's not really necessary to apply it. There are also direct solvers available in GRASS GIS. The Cholesky solver, which is kind of a lower and upper decomposition, but a kind of more efficient than the classical one. You all know, probably even from school times, the Gauss elimination scheme. Direct solvers are rather uncommon choice here because they require a significant amount of memory. So iterative solvers can operate on something like which is called a sparse matrix. So the matrix is mostly consisting of zeros, and you just have a few values written somewhere in your matrix. Direct solvers cannot work on sparse matrices. They work on the full matrix, so the full matrix need to be stored in memory, and this requires a substantial amount of RAM. As you know from previous lectures, well, is a critical hardware limiting factor for numerical simulations anyway. I also talk with you about supercomputing and supercomputing technologies. And also here, GRASS GIS supports parallel solutions of the partial differential equation, again, as part of its internal mathematical library to solve partial differential equations. The computing technique here, or the parallelization technique here, is based on OpenMP, which is a quite famous open source parallelization library. It's called Open Multiprocessing, so the open here relates to open source software. And it's a shared memory parallelization, right? So it is not computed, not used for real supercomputers or network operations, but more based on your single multi-core processor, which is, if you're using GRASS GIS for groundwater flow modeling, the usual case, because when you want to go professional, you would probably use some kind of other software or program the solution yourself. Interesting here is, or good to know, is for you the parallelization technique is thread safe, which means that you have a multiprocessor execution with automatic load balancing, without blocking or introducing error through the parallel solution. So this is already it. As I said, it's a very short introduction to the GRASS GIS groundwater flow modeling capabilities. As I said, it has a limited functionality. It requires a lot of user interaction compared to maybe more constraint or software which is more concentrated on groundwater flow modeling. But with this lecture, I hope you will be able to understand a bit the benefits and the drawbacks of the different solver types which you can choose, understand how iterative solvers work, and how you can associate the parameters that you can use for those, or you can specify for those iterative solvers, how those relate to accuracy of your numerical solution. Thank you very much.